September 11, 2025. While the world sleeps, a Ukrainian amateur catches what billion-dollar telescopes miss. A comet erupting with the brightness of 10,000 power stations. Its tail stretching wider than 5 full moons. This is Comet Swan. 400 times brighter and 200 times bigger in the sky than the legendary interstellar visitor 3I/Atlas, yet discoverable with nothing more than a pair of binoculars. For the first time, a backyard stargazer has outpaced the world's top astronomers, rewriting the playbook on cosmic discovery. But why did experts overlook a spectacle hiding in plain sight? And what does it mean when the brightest comet in years eclipses an interstellar intruder on the edge of a 47-day collision course? The answers redefine what the solar system keeps from us. And what comes next is more astonishing still. Vladimir Bezugi's nights rarely follow the clock. While most astronomers trust automated surveys to sweep the sky, he sits in front of a battered laptop, scrolling through hydrogen maps beamed down from the SHO spacecraft. On September 11, 2025, just after midnight UTC, a faint shifting blur caught his eye in the Virgo sector. A blue-green plume brightening in the latest SW difference images. Bezugli, a veteran of more than 20 comet finds, paused. The shape was no sensor glitch. Frame by frame, the cloud grew sharper, stretching wider than anything he'd logged before. Within minutes, he ran his custom scripts, flagged the anomaly and posted annotated screenshots to the Comet ML mailing list and Telegram's SW Watch channel. By 1:30 Universal Time Coordinated, he'd ruled out every known artifact and filed a formal report to the Minor Planet Center. The object's brightness, already near magnitude 7, meant it was visible to anyone with a basic pair of 50mm binoculars. That level of accessibility is almost unheard of in modern comet hunting, where most discoveries lurk far below the reach of amateur optics. Within hours, Martin Mashik's team at the Czech Fram telescope confirmed the sighting with ground-based images, and the international community sprang into action, trading coordinates and magnitude measurements across continents. Bezugli's workflow, mining daily SSW difference maps, scanning for moving hydrogen features, had just rewritten the rules. In a field dominated by billion-dollar telescopes, a single amateur's careful eye had spotted a spectacle hiding in plain sight. The democratization of discovery was no longer theory. It was a comet blazing across the sky, and anyone could find it if they knew where to look. 12 hours after its discovery, the comet's trajectory was already being mapped in detail. The numbers are staggering. On September 12, 2025, Swan sweeps past the Sun at just half an astronomical unit, about 75 million kilometers, or the distance from Earth to Venus. Then 5 weeks later, it threads even closer to Earth itself, passing within 0.26 astronomical units, 39 million kilometers on October 19. That's inside the orbit of Mercury and close enough for the comet's tail to stretch across 5 degrees of sky, rivaling the length of 10 full moons lined up edge to edge. But the orbital path is only part of the story. The comet's outgassing jets driven by sunlight hitting fresh ices are calculated to release energy at a rate of nearly 10,000 GW. That's not a typo. For comparison, the entire human race with every power plant running at full tilt barely manages the same output. In raw power, Swan is a floating engine room, pushing more energy into space than all the world's cities combined. These numbers aren't just academic. They set the stage for a rare spectacle. A comet bright enough for backyard binoculars, moving fast enough that its position on star charts shifts night by night. For astronomers, the countdown to perihelion is more than a calendar note. It's a race to capture every possible measurement before the comet's closest approach and before the next act in this cosmic event unfolds. Most people will never see 32/Atlas, not even with the best binoculars. Its brightness sits at magnitude 13.3, a number that sounds abstract, but in practical terms, it means the comet is about 360 times fainter than Swan. That's not a rounding error. It's a gulf. On the magnitude scale, every 5 steps means a 100-fold difference in brightness. So, while Swan blazes at the threshold of human eyesight, Atlas is buried deep in the background, out of reach for all but the largest backyard telescopes. The size gap is just as striking. Atlas's coma, the faint cloud around its core, spans only a few arcsec, barely larger than a distant star through a telescope. Swan, by comparison, stretches across whole degrees of sky. For most, Atlas will remain a number in a database, a target for professionals and dedicated amateurs with expensive gear. The exclusivity is built in not by design but by the physics of light and distance. This is a comet for the telescope elite. Speed alone sets 3I/Atlas apart from any comet in living memory. Tracked at 58 kilometers per second, it moves fast enough to cross the distance from New York to London in under 2 minutes. This is not a solar system wanderer. It's a true interstellar traveler, following a hyperbolic path that guarantees a one-way trip out of the sun's grasp. As Atlas approached perihelion at 1.36 astronomical units, about 203 million kilometers from the sun, European Southern Observatory teams turned the Very Large Telescope toward its faint core. The spectra revealed something unexpected. A chemical cocktail dominated by carbon dioxide with an 8-to-1 ratio over water vapor. Even more surprising, the data showed clear signatures of nickel vapor, an element rarely detected in comets and almost never in such abundance. These findings confirmed across independent observatories hint at a formation history far from our solar system. For planetary scientists, Atlas's faint glow conceals a trove of clues about the chemistry of other star systems. The excitement in the professional community is less about spectacle and more about the secrets locked inside this fast-moving exotic visitor. October 8 draws a hard line across the sky. Both Swan and Atlas slip behind the sun, dropping below 20 degrees of solar elongation, the minimum angle needed for any ground-based telescope to safely catch them. For 11 days, from October 8 to 18th, Earth's entire fleet of observatories is effectively blind. Even the most advanced instruments are powerless against the sun's glare. No images, no spectra, no real-time tracking. The blackout arrives at the worst possible moment. Just as Swan closes in on Earth and Atlas nears its own solar flyby, all the action, the jets, the evolving tails, if anything dramatic happens, it happens unobserved. The timing is merciless. The 47-day window between Swan's perihelion and Atlas's peaks is sliced in half by this invisible wall. Astronomers run simulations, check ephemerides, and share anxious forecasts across forums, but nothing breaks the silence. The sky holds its secrets until the comets re-emerge, leaving a gap in the record that no technology can fill. Disagreement is written into the orbit of Swan itself. At the Minor Planet Center, analysts fit the available data to a 1,400-year return period, suggesting a comet that will visit again within the span of recorded history. At NASA's JPL, the same object run through a different set of assumptions and a longer arc that includes low-precision prediscovery images stretches out to a staggering 20,000 years. The split, almost 19,000 years apart, reflects not rivalry, but the real limits of what can be known from just a few weeks of data before the comet vanished behind the sun. Both solutions are provisional. Each depends on how much trust is placed in faint pixels from stereo A or the reliability of a handful of ground-based points. As the blackout drags on, clone orbits and Monte Carlo simulations pile up in institutional servers. But the gap remains. This is not just an academic exercise. Every amateur with binoculars, every professional with access to a major observatory is part of a global campaign to pin down the truth. New reports flood in from Australia, Europe, the Americas. Each measurement uploaded to the Sky Live. Each image cross-checked in real time on community forums. Even as the blackout silences optical telescopes, the conversation never stops. Meanwhile, another player, Comet Lemon, slides into the scene, its own tail brightening to magnitude 4. For a few weeks, the sky becomes a shared laboratory, and every observer from backyard to research institute is a collaborator. The unanswered questions: how long Swan will be gone, what secrets it hides, whether the orbit is short or epic, become the engine of the story. Science here is not a set of answers but a living process, crowdsourced and unresolved. On September 11, 2025, Vladimir Bezuki used NASA's SOHO/SWAN instrument to identify a comet 400 times brighter and 200 times larger in the sky than the interstellar 3I/Atlas. As confirmed by the Czech Academy of Sciences and published magnitude data, Swan's 2 to 5 degrees tail and peak brightness of magnitude 6.22 made it visible to anyone with binoculars, while 3/Atlas, although the fastest interstellar visitor recorded at 58 kilometers per second, remained 360 times fainter and accessible only to advanced telescopes. Both objects vanished behind the sun for 10 days during their closest approaches, leaving a critical gap in observation. Disagreement between JPL and the Minor Planet Center over Swan's orbital period, ranging from 1,400 to over 20,000 years, remains unresolved. Despite global efforts and real-time tracking, key questions about why a magnitude 6 comet evaded earlier detection persist. This season, citizen scientists and professionals alike watched as nature delivered a rare convergence. A spectacle unmatched in brightness, scale, and mystery. all confirmed by independent observatories across 3 continents.